So this afternoon we are here to learn how to prepare a phase diagram when you cannot find it in literature. If you can find it in literature, it's much faster. You take the book, you open the book, and you pick up the phase diagram directly in the literature. Sometimes it doesn't exist because to mix three solvents, there is so many solvents and so many ways to mix them that there is a book this thick and the one you want is not there. So Gilda selected hexane, THF, and water as an example of phase diagram. So to prepare the phase diagram, we will use a ternary triangle. One apex, the lower left apex will be water, the right apex will be hexane, and the top apex will be THF. Why is so? It's because we are chemists and we know that water and hexane are not miscible. That's the two immiscible liquid. So I know if I make in a test tube hexane and water, I will get two phases. It's sure. Okay? Second step, we know that THF and water are miscible. Any proportion of THF and water give a single phase. That's second point. And third point, any proportion of THF and hexane also give a single phase. So we will obtain a type 1 diagram, which means this is a single phase, we are sure. This line is a single phase, we are sure also. And that line are two phases. We are also sure before starting. So we know that in this triangle area, we have some line that will make a boundary between two phases and one phase. Where is that line? So to find that line, we need titration. We need experimental measurement to find that line. So to find it, I don't know, I will start right in the middle, for example. I will start here. So let me make a point. This will be 50% THF, 50% water. 50-50, just in the middle of the THF water line. You remember we learned yesterday how to draw phase diagram, and starting at the middle, everybody agree this is the middle. No problem. And that's a property of the phase diagram. If I add drop of hexane in this mixture 50-50 THF water, the location of the final composition belongs to that line, going from the starting point 50-50 up to the hexane apex. We know it. So that's a good guide. We know it's belongs to that line. So I will add drops of hexane, just looking with my eye. Do I have one phases? I am in a one phases zone. Do I have one phases? No. I am in the two phases zone. And I will write down the point when it goes one phase to two phases. So let me draw the line with my ruler, special ruler. We know that adding hexane, we will move on that line. Okay, so let's do it practically. How much water THF mixture 50-50 should I prepare at the beginning? The answer is simple, I don't know. Good. So in this test tube, I will put a certain amount of water. This amount. Why not? Okay, and now I put this back in here. So, by chance, I didn't cheat. It's really, somebody want to read the numbering. It's exactly 193, almost 1.5 grams. It's not, it's by chance. So I write down the mass of water I got, water, H2O, 1.493 gram. Now I must put the same amount of THF. Is it absolutely required to put exactly the same amount? No. Yes, it's required if I want to do exactly the 50-50, but since you are drawing it, if it's 49-51, it's okay. If it's 51-49, it's okay. So you look to put about 1.493 gram of THF, but if it's not exactly that, it's okay. It will not be exactly that due to temperature, and THF, it's very volatile. So I'll try to put this amount, but I have no guarantees that I will get exactly this amount. So this is THF. I'll put THF, say, first. It's dripping alone. First, the same amount, putting 0 again. Okay. So I can start without one phase. By the way, you can check it's one phase. I don't know if you see it, but I do see it. It's one phase. Waiting. I have 105. Now to go on, I must add dropwise THF. I'll put some in here. 1.3, 1.4, 1.9. 4.2, 1.442. 1.495. Let's go this way. So 1.492, it's evaporating really quick. I should cover this tube. Okay, we'll ignore evaporation. It's no 1490. Okay. Let's take 1490. So I have my 50-50 mixture of water and THF. I check, it's one phases. Oh my goodness, a lot of bubble in there. So that's normal. When you mix organic solvent with water, you get a small heating and gas bubble. I don't know if you see them, but it's like carbonated water. So this is due to the fact that the gas are less soluble in the mixture THF water than in the pure solvents. So I remove those bubbles. I could remove them quick using ultrasonic bath, but we will just wait a little bit. Check that this stay at the correct weight. 1488. Okay, I lost 2 milligrams more. I'll put 0 on this. Okay, so that's my mixture. 50% water, 50% THF, here, this point. Now I will drop hexane in this test tube, drop by drop. This is water, this is hexane. Oh, I can use stupid. I will drop hexane in the mixture, weighting it. So I'll weight how much hexane I have in my mixture to know when it's one phase. So I guess now it's clear, no more bubble. So let's take, I don't know when it will make two phases, so I have to be very slow, one drop. You see the drops dissolving, making cloud, and the cloud disappear. It's solubilized. I am solubilizing hexane in this water THF mixture. It's clear. It's maybe difficult to see, but it's still clear. Put a second drop. When I put the drop, you see some cloud. The one this is cloudy. So let's be careful and wait. I think that's it. That's it. Two drops, I get two phases. So why it's cloudy? Because there is very small amount of hexane that saturate itself in, and now you can see the two layers. I don't know if you see them, but there is a thin layer of hexane at the top. So that was really quick. I waited, and we have 0.025 of hexane. So I write down this, 0.025 gram of hexane makes two phases. So this is the binodal composition, and actually I even pass it a little bit because I have a thin layer. See the cloud? And when I let it separate, you see a thin layer at the top of hexane. So we are in the biphasic area. So that's, now we finish the calculation. Okay, now I have this total of, I don't know if you see it, I have this total. I have to calculate percentage of each compared to this total. It's really easy. Percentage of water in 3008 gram is 1.493 divided by 3008. So you see 49.6, 49.53, 0.83. I cannot draw this on my handmade diagram. I would need a very accurate handmade diagram. I just put a big dot here, but the dot is 2% wide. So it's right here. See, less than 1% of heptane. You remember we read heptane on the basis which is parallel to the heptane apex. So that's 0.1%, less than 1%. It's very, very, very close here. So I will not have the trouble to make those. It's all probably, if you put more water in the initial mixture, you will get less hexane soluble. So my binodal curve is just very close to that basis line, and I will go now, I'll go 9 to 1 to make the second one, to have a little room to put some hexane in it. Because this, you have seen 2 drops, and I got 2 phases. It's still there. So it means hexane is very little soluble in THF water 50-50% mixture. Okay. So now I'll make a second one if you have no question. And I will go there on 90%. Let's make 90% THF and 10% water as initial composition. A point very close to the THF apex. Let's save this one there, and I take a second tube. This much will do, THF. Could put this one, weight it, write it down. and I read 533, it's evaporating. Okay, we'll put THF a little bit more, 2.533 gram. Okay, so 2.533, this is 90% of my composition. Divided by 0.9 multiplied by 0.1 is 0.281 gram of water to get 90%, 10% exactly. I will try to make 0.281 gram, which I should start right away with drops of water because it's really small. This one was xn. Let's put it back here. .281, 0 again, and I will drop 0.281 water in this tube. It's 0, yes. Point 1. 0.14, 281, 24, 27, up, 282, will do. So water 0.28. That's strange, it's 4 now. That's 2. 0.282. And now I am adding xn in this mixture to get the end of the line. Checking the tube. Okay. We have in this tube for the line 90% THF. THF 2.593 gram, water 0.282 gram, and xn I will check up to seeing two phases or a cloudy tube. This tube is clear. So water, we knew it, it's completely miscible in THF. Actually, it's just drop in the bottom, and I should check it carefully to be sure I have a homogeneous mixture. I have much less bubble because this is very close to pure THF, 10% water in the THF. So the gas solubility is not that different from 50-50, which was the most different you can go between water and THF. So this is the mixture. I will check again the weight. So that's a 0.281 now. I say it's okay. Put 0 to have the reference value. And I will start to add, which one is it? This one in xn. So I take heptane, xn actually, oops. Doesn't stay it's very warm here. It doesn't stay in the pipette. I'm glad nobody got it. So 0. I put a drop. Soluble. 2 drop. 1 phase, clear. I hope you see it. I think on the screen you see less than real in real. I'll put 2 more. Clear. I can wait to have the gram amount I put. I am at 0.06 gram of hexane. So it's already 2 times more than we did the previous line. I go on to 3 more drops. I see a cloud at the top. I shake. It's clear. 3 more drops. It's clear. 3 more drops. You'll see it's very, so interesting. I could make the music. Pom, 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 pom. I can see cloud going at the top of the tube. I'll go. I'm not counting drops anymore. You see, I'm pouring hexane in it. I had see the cloud forming at the top, but when you shake it well, let's see. It stays cloudy. But sometimes it takes a little while to equilibrate. I check temperature. Temperature is okay. No, I think this is this stay cloudy. So I'll wait it, and when I wait, hopefully I will start to see decantation in 2 phases. So this is 0.301, 0.300, and now it's 0.299, 0.300 gram. But 0.300 gram. You see, it's cloudy, and I don't have 2 phases, which means I am really just on the binodal curve. I don't see 2 layers. On that one, now you can clearly see the 2 layers. So even though I put less than 0.3%, I passed it. This I didn't pass it. It's just not clear. It's, I don't know if you see it better. No, you don't see it. It looks white. But it's not completely transparent. I'll wait it again, and I will pass on purpose the point to show the 2 phases. So that's 0.300 confirmed. Okay? So that's the binodal composition. I will pass it to be sure with 3 or 4 drops. And now it's starting to make 2 phases, but for information, this point has no interest. I just pass it 0.34, that's not much. I think I see a very, very small drop of heavy phase at the bottom. I'll go a little bit more to be sure. 1, 2, 3, 4, 5, 6. Yes. So let's settle the things. 0.47. Meanwhile, I'll make calculation on that composition. So we got binodal curves weighting 2.533 grams of THF, 0.282 gram of water and 0.300 gram of hexane. I will sum this to have the mass, total mass, and calculate the percentage. 81.32%. 0.282 divided by memory is 9.05%, and 0.3 divided by memory is 9.6. It's the same? Oh yeah, 2.8, 3.0, 9.63% weight. I found that total mass is 3.115 gram, which make 81% of THF. The 0.28 of water make 9% of water in this composition, and the 0.3% of hexane, approximately the same, make 9.6% in weight percentage of hexane in the proportion that give two phases. So where is this point located? You have to draw a line that goes from the 90% THF up to the hexane apex. So let's take the ruler, draw the line. Okay, these lines tell me that I should go 9.6% hexane on my poor triangle drawn by hand. It's difficult. I would say 50% is there, 25% is there, 9% approximately here. You see, this is the limit between one phase and two phases. So now I got 2 points. It's not enough to guess where is my binodal curve. So what I can do now is take THF and hexane and add water in it to make a line this way. So I think I have to put a relatively large amount of THF. So let's try a kind of 80% THF, 20% hexane, unless you want another one. You know, then I can estimate part of my binodal curve in dot, in dash actually. I have part of my line very close to this baseline, THF water, going to around here. Is it this? Is it going this way? I don't know. I should check making line this direction. So if I prepare 80%, I would say 80% is right here, approximately, and of THF, 20% of hexane, and I add water in it, I will cross the line after a few drops, after a certain mass of water added to that composition. That will give me one more point, allowing a better curvature estimation of the line. And then there is no limit. You can do 4, 5, 6, 7 line up to have the most accuracy possible on the diagram, on the phase diagram. When I was talking, we let this one rest. Let's have a look now. It's very difficult to see, but I do have a drop at the bottom. I have a drop of heavy phase, and most of the light phase is on the top of it. So you don't see it. I may have to pass the tube to see it. But there is a drop of heavy phase, a clear drop of heavy phase at the bottom. So we do have two phases in this one. And I remind you that I pass the cloudy proportion a lot. Okay? So let's go third time, and I guess will be enough after you will understand everything. So now I prepare for the first composition the line which will be 80% THF and 20% hexane. And adding water to that line, we are moving from the initial composition toward the water apex. So I'll prepare this composition, and we are moving towards that apex, water. And at certain time, we will cross the binodal curve. That will be clear, clear, clear. At the drop we cross, it becomes cloudy. So I will know where this line is. This dot line, it's an estimate I just put. So let's check. Third tubes, this one. 0 again. So we say 80% THF. I can use that one. Is this 0? Yes. How much THF you put? This much. That's too much to put everything. This much, for example, will do. This much is exactly, I'll start another page. THF 2.338 gram. So this is 80% of my composition. I want this so. So I take 2.338, divided it by 0.8, which is 80%. That gives me total mass, and multiply by 0.2, which is 20% of hexane, and that gives me 0.584 mass of hexane I should put in to start 80% THF, 20% hexane proportion, 0.584 gram. Look where I put the hexane. This is it. Yes, this is it. No, there is enough remaining. 0.584. Point 1, 0.2, will not make it. Okay, I'm dry. 0.46, and I need 0.58, so I have to take more, little bit more, there. So 0.584, 47, 49, 50, 2, 4, 6, 7, one more. 86. 86 will do. Okay. Oh, just let's wait a little bit. And now it's at 5. 0.585. 0.584. I got it. That's it. You don't see it, but I can see the two layers of THF and hexane at the top, because it's different refractive index. I don't know if it shows on the movie, but I see it by eyes. So I have to shake. I shake, and I get a clear solution without any bubbles. Okay, clear solution, which is 0.584. Good. Put 0 again, and now I will drop water in this mixture. This is water. Yes. So that's clear. I put 1 drop of water in it because I think it's very close when we get 2 phases. Okay, the water drop went right to the bottom, and now I see it, but I don't know if I will be able to dissolve it. It's still there. I am afraid to lose some mass of it. Maybe it disappeared. I should check it. Yeah, I think it disappeared. This is much more difficult to see because you get a drop going at the bottom directly, not making a clear cloud, and now you have to check if this drop disappeared or not. I think it disappeared. I don't see anything more. So I go for a second drop. Yeah. There I see it clearly. So the good tool would be ultrasonic vibrating machine to be sure you mix it very well. I think the second drop disappeared also. Yes. Third drop. I have bubbles there. Third drop. Still there. Yeah, still there. So I'm going to wait that one. At this point, we are at 0.076. But I'm not sure if it's the right point. I write it down, and if it's not good, I'll crash it off and take the next one. I think I see micro droplet remaining. I know you see nothing. The top layer is very clear, but I see very teeny droplet flowing in this tube. So I may be at the limit. I'll go for one more drop to be sure. Yeah, this is clearly making, you can see the cloud forming, and the little drop goes down. So this is passed. I'll wait this one also to see the variation. Any measurement, you have a variation. And this is 0.088. I write it down also 0.088 gram. But I will do calculation with 0.076. So yeah, this one has a kind of cloudy aspect. It's no more 100% clear, so let's make the calculation. So this is the initial mass of THF. This is the initial mass of hexane, didn't change. And we add 0.076 gram of water. It could be, that's the second one, which is actually in this tube, but I think it's a little bit past. You see the change that's make. If you make calculation with this mass instead of that one, I will change the second decimal, not the first, I think. So this mass is 77.98% of THF, 78% THF. And we have 19.5% of hexane and 2.5% of water. That's the binodal composition for 80% THF, 20% water. So we put this on the phase diagram. 2%, it's approximately here. So my guess was too optimistic. The real tie line goes more this way. And since I know it's finishing there, I will not make a fourth one. You're welcome to do it if you want. I will draw the binodal curve this way with a continuous line. And we got our ternary phase diagram. It's a little quick with only 3 experiments and 1 hour. But this is it. This diagram, water, hexane, THF, has a large area of possible work in CCC. You really need to put more than 80% THF to get 1 phases. Most of the other composition, you have 2 phases. Okay, on this binodal curve determination, now, if you would like to have an idea of the tie lines, where are the tie lines? Are they horizontal? Are they sideways? Which way? This way? This way? This, you don't know. You have to analyze the composition of the top phase and bottom phase. I check that I still have, yeah, I clearly have a droplet at the bottom on that one now. So to have an idea of the tie line, I will prepare, I will prepare a composition somewhere in the diagram. Say, I can prepare a little bit, not in the middle, a little bit on, let's say on the water side, since water is the less expensive solvent, that would be better. So let's prepare, if I prepare 50% water, 30% THF, and 20% hexane. I will try to put it by hand, it's difficult. 50% water would be on that line. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. On that line, 30% THF would be approximately here. If I prepare this composition, which is 50% water, 30% THF, 20% xn. No, I'm wrong. 50% water, 30%, it's lower. It's difficult on such 50% water on that line, 30% THF, THF 100% is there. These are the THF line, but I have just 8, no, not 10, so I am guessing. 30% THF and 20% XN, this is wrong, 20% XN, I put too much. I would need a real calibrated diagram and a ruler. I'm sorry to do it by hand on this. But that still, I can prepare this in another tube, 4 mils of water. I'll adjust it exactly to 4 mils. Where is my water? This and this. There. And weight it. It's 4.274. Saying 4 mil. I'll still go weighting. 4.274 gram. Then I go 30% THF, which will be 4.275 divided by 0.5 is 855 times 0.3. I need 256 gram of THF. THF, 266 gram, may not have enough. $266 gram of THF. I forgot the 0. Okay, 0, 266 gram. That's probably more than 2 centimeters. One. 1.4. Two 56. THF 30%. 256. 31. 45. 56. Will do. Okay. How many phases? 2. I see the limit here. Strange. I thought THF and water were miscible. There is 2 phases. But if I check it, it disappears. We have no time. Do we have something I could? Because this kind of tubing has a good graduation, but it's not very good to shake. You still see the 2 mixture. So that's my fault. I should put THF first and water that goes through second. I didn't, so THF just went up to the water And now I start to shake. You don't see any more meniscus, but you have, this is pure water at the bottom, pure THF at the top, and you have a gradient of concentration going from 0 mils to 7 mils here. That's no problem. Since I have to shake anyway when I will put hexane, I'll put hexane in this. With the problem that hexane is even lighter, I got the density somewhere through Susanna. Yeah, hexane is 0.65 gram per milliliters, and THF is 0.88 gram per milliliters, and water, of course, is 1 gram per milliliter. So it doesn't matter. I will put THF, hexane on the top. So this is water, it's done, and now I'll put hexane. And how much hexane should I put in? I have to calculate. I have to put 855 times 0.2 is 171. 1.71. Just two numbers? Yes. 20% hexane is 171 gram. So you understand what I am doing now. I am preparing a special composition in this location in the phase diagram we just delineate. So I am sure this composition should be two phases, because it's, by definition, if it's below the binodal curve, it's two phases. This is one phase, this is two phases. So I have one phases now because I have just two solvents mixed. Now I have to add 2.171 gram of hexane to make 20%. I forgot the 0, and 1 gram 71. I'll cheat a little bit. 171 divided by 0.65 make 2.6 milliliters. So I can go right away to 9.6. Oops. 9.6. And then I'm going to wait. There. Okay. This is 1.4, and I go to 1.71. I will go for 171 drop by drop. One 1.6, 5, 6, 1.67, 1.707, 1.716. Okay, that will do. Now you can see a clear meniscus. That's not the right one. This is between water and THF and hexane. So this, I have to shake it very carefully, checking the volume, the total volume in that, how you call this, cylinder? I have to put it on the table. It's 9.6 milliliters total. Now I should read where the meniscus is, and for this I should clearly check it very well. And I don't know if it shows on the movie, but you can see the hexane going down in the THF phases at the meniscus. This is not a true meniscus. It's not equilibrated. You see the change in, I don't know if you can see it, but there is, it looks like hair going in the other phase. And that's not, that's because it's not equilibrated. So this meniscus is located at 5.8 milliliters. This you can see it if I turn it right. There. You see the meniscus at 5.8 and the 9.6 milliliters total volume. Okay, it looks to be 9.7 on the screen because it's not vertical. So what I do, I shake the mixture with the pipette, which probably use as much solvents that my finger would do. But you know, the problem is a little part of the mixture stay in the pipette and make mistake in the volume. But that's what, for what we are doing, I will do. It's okay. So now you're sure you have two phases, because I shake it as I can pick up the upper phase and put it in the lower phase to be sure it's well shaked, and pick up the lower phase and put it in the upper phase. So I'm sure it's approximately well mixed. Problem is I have small amount staying in the pipette. Okay, I can check. If I have 9.55 instead of 9.6, I know where the mistake is coming from. I do have 9.5. Okay. Yeah, that's okay. Now, what I do, I read this meniscus position, which is thick. I'll wait a little bit to be sure it's separate well. And now the new position of the meniscus is at 5.1. So I write down, I have 9.6 milliliters, lower phase 5.1 milliliters, upper phase 4.5 milliliters. Okay, whereas you can see the numbering there. Okay, so lower phase up to here, 5.1 milliliters, and upper phase 4.5 milliliters. Okay, so it means the point I prepare, 50%, 30%, 20%, is located in the tie line at a position which correspond. I should make a new drawing. By hand, we have no time, okay? Okay, I prepare a composition, say 50% water, 30% THF, 20% hexane. I can see the amount of upper phase and amount of lower phase. And I know the amount of upper phase time, suppose the tie line is like this. Suppose. I don't know. We'll see. I know that's the amount of upper phase times this distance is equal to the amount of lower phase times this distance. So in that case, I would have a big difference between upper phase and lower phase because the point is very much not in the middle. Now, with what we got, I got this. Lower phase 5.1 mils, upper phase 4.5 mils. So it's close. So my point is close to the middle of the tie line. So I can calculate, it has no meaning with the little drawing I did by hand. Close to the middle would say it's approximately an horizontal tie line. But when you do it carefully with millimetric papers, you can really find the positions that will exactly fit 5.1 millimeters times this distance from the point on the binodal curve to the point you prepare equal 4.5, which is a little bit smaller, so the distance is a little bit bigger, time this distance to the other side of the tie line. You can find only one line that will have this relationship obeyed. All other lines, it's too short on the one side and too long on the other. Only one line has approximately exactly the right value. 51 time distance on the left, 4.5 time distance on the right. Okay, so this is to give you indication. The best is to take the upper phase in the gas chromatogram, inject, and get the peak area of THF. We have hexane is very easy to determine by gas chromatography and THF also. Get the peak area of the two. Same with the lower phase, get the peak area of the two, and then you have the composition. And if you need water, the technique is called Carl Fischer. You can take a little amount, a known amount of upper phase and get the Carl Fischer titration, giving you the water proportion, and same for the bottom phase, and you have the exact amount of the phase that you can put on your phase diagram, and it is required that the composition you get there, the composition you get there, and the 50, 20, 30 we prepare, all three are aligned. That's the tie line definition. And usually, if there is no error in the measurement, it works pretty well. That's it for what I wanted to say on the phase diagram. I know there is a lot of calculation, but it's not very difficult once you make one or two. It's really doable by student in one day. Questions? The temperature is really important. That's true. This is isotherm phase diagram. When it's a phase diagram published in a physical chemistry journal, it says temperature 20 degrees, temperature 25 degrees. You do have differences. The binodal line change if it's warmer or if it's cooler. On my own observation in CCC, it doesn't change significantly on the drawing. Why? You see this dot we did on the first experiment. We found 0.8%, if I remember. That's the next page. 0.8%, we found 0.8% hexane. When you draw the line with your pencil, the line itself is approximately 0.5% wide. So you would make at 25 degrees, it would be difficult to see the difference. Of course, I am an analytical chemist. A PChem chemist would say, wow, it should be very carefully regulated in temperature. But if you work that way, you cannot do anything. So, since you have this question, I will tell you that what we did here, it's mass phase diagram. We use mass, okay? Because it's convenient to show and click, it becomes to 0. That's very easy. You can go volume phase diagram. A PChem chemist will tell you, no, 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 when you mix hexane and heptane, 1 mils plus 1 mils, it's not 2 mils. How much is it? It's 200.15. Okay. For me, analytical chemist, it's 2 mils. If this phase diagram we did in mass, I want to have it in volume, because when you work, you prefer volume, measure volume, you will calculate all masses I wrote there, convert in volume. I can do one if you want for water, it will be easy for me. You want to convert 1.493 grams of water in milliliters. Since the density of water is 1, that's 1.493 milliliters. Okay? Then the second one is 1.49 gram. Yeah, it was a 50-50 line. So that's the same mass in THF. This is not 1.49 gram, 1.49 milliliters. THF is 1.88. I need, again, my calculator on my Excel computer software, if you prefer. And 1.49 gram of THF make exactly 1.68 milliliters. 1.68 milliliters. And same with hexane. 0.025 gram make a little bit more in milliliters. Then you add the volumes. Instead to make the total mass, you make the total volume, and you have the percentage in volume. And you can work and draw the same diagram that will be a volume diagram. It's not very different from the mass diagram. It's a little bit different. Then, drawing it, you can see the difference. If you go mole, because you can go mole, I can say 1.493 gram of water. You know that molar mass of water is 18. It's 1.493 divided by 18. This is 83 millimole of water. And that's a certain amount of millimole of THF and millimole of hexane. I can sum the millimoles and work in percentage, molar percentage. And this is very different as phase diagram, because 18 is very small and give a lot of molecules in a small amount of water, much less molecule in the same amount of THF. So in percentage, you see the water space expanding dramatically. So for your question about temperature, yes, temperature is very, very important. But as long as you have water in the system, in CCC, which is 90%, maybe 99%, I don't know, of the phase diagram we use, it's not critical as long as it's between 18 degrees and, say, 28. So on this 10 degrees temperature range, the phase diagram you can find in books is valid. You can work with that. The pH? In that case, you mean if you want to buffer the THF water system, yes, it will have an influence, but it's not the pH. It's the ionic strength that will have an influence. If you put salt in water, you get a physical chemistry effect which is called salting out. If you put salt in water, the salt is pushing everything organic which is dissolved in water in the organic phase. So it would move this line even closer to the border, making even less hexane in the system. But this is true if you go 10 grams per liter. When you buffer, you go 10 to the minus 3 molar, which is less than 1 gram per liter. So it's, again, it would change the line in a way you won't notice the effect. So it's not critical. You can work with buffering the THF water system with no problem. It will work.
Thinking about the gradient system, I could predict what will happen. Think about the variation that the systems goes through.
Yeah, so this is not part of this course, but why is it useful, this kind of diagram? If you have a very long tie line, which seems to be the case in this diagram, if you have a very long tie line, it means the composition of one phase is completely different from the composition of the other phase. So you will have partitioning that are likely, I just go in that phase and not at all in the other one. It will be difficult with a long tie line to have partition coefficient close to 1, small partition coefficient. You will have extremely small partition coefficient, 0.01, and the other compound will have 12 or 20. And you will try, how can I get the partition coefficient closer to 1? The answer is, in this diagram, you have to go with a tie line which is smaller, which means put more THF. If you put more THF, and if the one we estimate is a little bit like this, you go with shorter tie lines, and you are more likely to have less difference between the two phases, and your compound will partition better. So the coefficient, the partition constant will decrease, getting closer to 1, and you have more chance to be able to work with this system. So there is no rule, because sometimes you want a big difference in partition coefficient. I want to extract all the fatty things which are very apolar from my polar molecule. So then you don't need a CCC machine. You can do it extracting. Very often you extract the compound you don't want, and you keep the other one in the other phase, because the partition coefficients are really different. But if you want to partition similar compound, you may have to work with smaller tie lines. So that's, in that case, smaller tie lines means a lot of THF. You have many phase diagrams that are more lower, so you can work with less common solvent, and that would be easier to butanol. We have a case which is butanol, water, maybe ethyl acetate. Butanol acid acidic water is just very low. As soon as you put too much acetic acid, you have one phases. So you should be very low in acetic acid, and that makes short tie lines.